So in the last video, we defined the Zariski tangent space, and then in the definition, we assumed that the tangent space to this variety, the variety that we want to compute, is contained inside AN, and A is the origin. So the question in this video is, how do we know that this vector space that we defined, for example, its dimension, how do we know it's independent of the choices that we made? So we want to have a more intrinsic description of this in terms of functions on the variety X. And so the next lemma is the first step in this direction, which says, well, if we're still in the situation that we like X is affine and A is the origin, then we can look at this I of A, which we also called Ix of A, which inside A of X, inside the coordinate ring of X, is the ideal generated by the coordinate function, because these cut out this point A, the origin. Then the claim is we have a natural isomorphism of K vector spaces from this K vector space I of A modulo I of A squared. So somehow this is the square of this ideal inside the ring A of X. We can take this quotient vector space. And the claim is isomorphic to the homomorphisms over K from TA of X to K, which is the dual vector space of TA of X. And then since this is clearly a finite dimensional space, this is also finite dimensional space. And then for these, we can take the dual space on both sides. And then the double dual here is just isomorphic to TA of X itself. And this is then isomorphic to the dual of this quotient. So this is the first step in the direction that we like, because it describes TA of X as a certain vector space associated to functions on X. In this case, functions on X vanishing at the point A. Okay. And so to do this, let's go through the proof. And as always, we just want to define, first of all, a map from one side to the other. And we first define a map from I of A to this side, and then we show that this I of A squared is the kernel. So the map that we want to define here takes an element of I of A, which means it's an equivalent class f bar of a polynomial f, and it sends it to a homomorphism from TA of X to K, which is just, well, you take the linear part of f. So you pick some representative, take the linear part. This would be a linear polynomial on AN, and then you can restrict it to the subspace TA of X. This is the whole map. And then we want to show that this is indeed, well, first of all, well-defined and surjective. So somehow let's see that it is well-defined. So for this, let's say we pick a different representative, right? That's the problem that we have. Let's say f bar is equal to f plus h bar. So this is a different representative. And if you recall, I mean, this I of A, this is a subset of A of X. So somehow this means we replace it by a different function in A of X. So in other words, the difference that we have here, this h, is a function vanishing on all of X. So it's an I of big X. Then by definition, well, this h1 restricted to TA of X is 0, because TA of X is cut out by all of the linear parts of elements of I of X. And so we see that, well, that F1 restricted to TA of X is equal to F1 plus H1 restricted to TA of X. So, and this thing here is essentially, by definition, of TA of X. So we did write down a well-defined map. And now for surjectivity, Well, assume that we have G on the right-hand side. So we have an element in K of TAX K. So this is a linear map from TA to K. Then what we can do first of all is we can extend this linear map in some arbitrary way to all of AN. Because TA of X sits inside AN, and we just extend the linear map from the subspace to the full space. But then a linear map from AN to K we can consider as just a linear polynomial, right? And then so we see this G extend. We can see kind of G and K of x1 up to xn as a linear polynomial. And then we have that it's a linear polynomial without constant term because, well, at the origin, this vanishes as a k-linear homomorphism. And so we have that its equivalence class in A of A satisfies that G is equal to G1. And so the image of this G bar under the map phi is exactly the thing that we started with. Okay. So this shows we can reach any element in here from an element in here. Okay. And then by the isomorphism theorem, so we have surjective linear map. And so the image is isomorphic to the domain modulo the kernel. We want to show that the image is isomorphic to this domain modulo this thing here. So it suffices to show that kernel of phi is equal to I of A squared. And one direction of this is very easy. Namely, if you have an element in the square of I of A, so in other words, if you have, let's say, F bar and G bar in I of A, and then you look at what, you take that product and you have all the elements of I of A squared are generated as combinations of such things, and you want to know what is the linear part, then, well, you can apply this formula. You get the degree 0 part of F times the degree 1 part of G plus the degree 0 part of G times the degree 1 part of F. But, well, F and G vanish at the origin. So this means this here is 0, this here is 0. And so this whole sum is actually 0, even before restricting it to the tangent space. And so clearly phi of Fg bar is equal to 0. This shows anything in IA squared is in the kernel. This comes kind of from the fact that if you take two things vanishing at the origin, you take that product, then there's no linear terms which survive. Okay. So the other one is a bit, this inclusion here is a bit more tricky, but it's basically just some fancy linear algebra, I would say. So to start this fancy linear algebra, let me define the following space. It's just you take all the elements in the ideal of X and take their linear part. This is contained inside the k-linear span of all of these x1 up to xn. I mean, all of these are linear polynomials. Let's call this span here V. And I mean, you can see V just as the dual space of k to the n. Right? So these are just linear polynomials. They sit inside this span here. And clearly this W is closed under multiplying by constants and addition. So it's a linear space. So let's say this has some dimension k. Let's call this dimension k. this full span has dimension n. Okay. We're going to see in a bit why we care about these things. Because now let's start approaching what we actually want, namely the tangent space, because this TA of x, this is the zero locus of W. And so this gives some set of linear equations cutting out this TA of x. And so if you start cutting it out from an, from n-dimensional space, and then if you impose k conditions, then you get something of dimension n minus k. And then if you take kind of the orthogonal complement in the following sense, so if you take the set of H in B such that H restricted to the tangent space is 0, the linear polynomial is restricting to 0 on the tangent space, then, well, taking the orthogonal complement, you again get the complementary dimension. So this is of dimension k again. And clearly, it contains W, because all of these have the property, by definition of TA, that they restrict to 0 on there. And so these two properties, if you're a k-dimensional space containing the k-dimensional space W, then you have the TAX dual is equal to W. So this was just some fancy linear algebra to show that this space here is actually agrees with the space of functions vanishing on TA of x. So, and now that we have this, let's say, now we actually start approaching this problem. Let's say we have an element in the kernel. So let's say f bar is in the kernel of phi. So in other words, f1, by the definition of phi, is f1 restricted to TA of x is 0. And so this is why we care about this TA x perp, because this is just equivalent to saying that this here is in this dual space. And so because this here is W, it means that we find some G inside I of x, such that G1 is equal to F1, right? And now we start being in business, because then F minus G, so somehow both F and G vanish already at the origin. So clearly this has no constant term, but it also, because they have the same linear term once you subtract them from each other, and it also doesn't have a linear term. So if you take some polynomials representing this, then the smallest degree terms that you can have start with quadratic terms. And then you just conclude that f bar, you can always, inside a of x, replace f by adding a function which vanishes on x. And so this is the same thing as f minus g bar. So this is just because g vanishes on x. And then this here is a polynomial with no constant and linear term. And then the claim is this is just an IA squared. And this is what we wanted, that this element of the kernel is contained in here. And here we just used that this IA squared is just a set of polynomials h with h0 equals h1 equals 0. So because the IA squared is generated, so somehow the IA is generated by these things here, And then I squared is generated by the monomials of degree at least 2. And so this f minus g can be expressed in terms of these. Okay. So, I mean, this wasn't a super insightful proof, but we now have seen that we get this isomorphism here. Okay. So this is already a good a step in the right direction, so to speak, because now we express this tangent space as this dual. But still, you know, we have in the lemma this assumption that x is affine and a is 0. So we want to get rid of this, and so we want a more intrinsic description. And the key idea is that we can reformulate this statement using the local ring. And the local ring of x at the point A, this is independent of any affine neighborhoods. And so once we have this description, we see that the tangent space is intrinsic. So to do that, recall that when we are an affine variety, then we can compute this tangent space pretty easily because it's just the localization of the full coordinate ring at the set S, which is just the coordinate ring minus the ideal of A. That was how you could calculate this local ring. And then it is also, like from commutative algebra point of view, it is a local ring. And the maximal ideal, you can call it IA, and this is the localization of the ideal I of A. And you can express it as the set of quotients G divided by F, where these are functions on X such that G vanishes at A and F doesn't vanish at A. Okay. And then with these notations as above inside this local ring, we have that the quotient that we cared about here, the I of A and modulo I of A squared from the last lemma, is isomorphic as a k-vector space to this S inverse of IA modulo S inverse of IA squared. And you see this is now a purely intrinsic description. So if X is a variety and A is an X, and then this here is the maximal ideal inside this local ring, then the tangent space at A of X is just given by its maximal ideal modulo its squared, and then take the dual. And this is sometimes also called the Zariski tangent space in commutative algebra. We see it independent of choices, and so in particular, its dimension is an intrinsic invariant. Okay, and here I just want to go through the proof a bit more quickly. The crucial thing I claim that we need to do is we need to show that multiplying by an element f inside this S, so this S was A of X minus IA, multiplying by such an element is invertible on this module here. Okay. If we show this, this claim star, then we first of all get an isomorphism. This module here is isomorphic to its localization at S, because I mean all of these things act as invertible multiplications on here, and so localizing actually doesn't change anything. So this already uses something from commutative algebra. So we get the localization of this module, and then there is a statement from commutative algebra. I mean, you find it in Gartman's script on the topic, which says that localizing and taking quotients commutes in this way that you can also first localize and then take the quotient. And you see, then we arrive at the right-hand side. So clearly, once we show this star, our proof is finished. And this basically just uses this kind of commutative algebra fact. And so the only thing we need to show is that we can find an inverse to multiplication by f. So S was the functions ax minus I of x. So in other words, these are exactly the functions which do not vanish at A. And so this means f of A is non-zero inside, also inside this quotient here. But the A, I mean, I of A is a maximal ideal inside here. and the quotient is exactly isomorphic to K itself. And the isomorphism was given by evaluation at A. And so this explains this here. And so this means, since this is non-zero in this field, we can find an inverse element. Let's call it C inside here. And in fact, I mean, under this isomorphism, you can just take C to be the constant function, which is 1 over the value of f at A, if you like. And then, well, we just want to see on this module here, multiplication by f is invertible. So when you have G inside this module, then we want to show what is G divided by f. We want to see this is a well-defined element, but then 1 over f is equal to C, and so this G over f is just C times G inside this module here. And here we use the fact that this here is not just an A of x module. I mean, I of A was an A of x module, and then if you quotient by the submodule, you get an A of x module. But in fact, it has a well-defined module structure also on A of x modulo I of A, right? Because if you have an element of I of A and you multiply with an element here, then you land in the I of A squared, which you divided out. And so you can, I mean, if you want, you can write this down for yourself, that if you have an element here, then you can write down a well-defined product independent of all choices. And so we can multiply by this C in here, and we get a well-defined element like this. And this proves this star, and as we have seen, the star was the ingredient that we needed to prove the corollary. And so this shows that we're done here. And so we have this intrinsic description. And using this intrinsic description, you can actually show something which is geometrically very plausible if you have maybe taken a lecture in differential geometry, or maybe even just seen this in some analysis lecture. There is the following statement, and if you have a morphism of varieties and A in the domain, then we get a linear map, which is the tangent space to this morphism at the point A. And it starts with a tangent vector of x at A, like this. And it takes the image of this tangent vector under the map. So you get a tangent vector here in the target y at the point f of A. And yeah, and using this description here of these two tangent spaces, it's actually quite easy to write down what this T of f is doing. Okay. That's everything about the intrinsic description of tangent spaces, and now also the maps on tangent spaces induced by morphisms.